allow me to introduce Adolfy Hoisie, which is another example of how a friend introduced a friend. So we literally were in the same table in supercomputing. It was actually a lunch provided by a vendor, the Orange guys, Evident, with the reinvention of Atos, which they thought is a good idea to become Orange. So, and I was there, free lunch, of course, but trying to convince them to come here or sponsor or whatever. And our friend Shaheen Khan, I just knew this, besides him, Adolfy was there. And guess what I did? What I always do. Here's a flyer. He actually read it. And he thought, oh, actually, this is cool. And here we are. And that's the power of personal marketing.
All right. Thanks for the introduction. It wasn't a breakfast, it was a lunch. But it was Shaheen Khan, whom I know since immemorial times ago. So, happy to be here, despite the uneventful way in which I made it here. I am known for taking directions well, so since you asked to reminisce or say something about me that nobody else knows, so I have one that may require action item from you. Because, it's something that not only you don't know, but I didn't know until very, very recently, like an hour ago, that my talk is going to be in the area of continuum computing. Never, ever heard this word. And so in a lab where I worked many years ago, and there are some people here that worked at the same place, we used to call this proof by assertion. So if you stated something 3 times, then the theorem was proven. So I said that 3 times, so I'm an expert in continuum computing. The other thing that I do actually, then that doesn't need to make it into the record book of multicore, is that if I had time and money, I would fly much more than I do. I fly single-engine airplanes. I wish I can fly here over Antarctica, but I get to fly now over the crowded airspace of New York and Long Island, and where the number of aircraft in the air is the same density as the number of cars on Long Island Expressway. So it's some kind of entertainment. So let's see. I'm going to give you a whirlwind on this field that I work in, called modeling and simulation. Most of the people here work one way or another in modeling and simulation, so I'll try to explain what my kind of modeling and simulation is. I'm not the only one that does modeling and simulation to characterize the computer in the application as an object. There are some important experts in audience, but nevertheless, it's an overloaded terminology, so I'll try to explain a little bit what's going on. And to make some sense of what I said about continuum computing, again, for real, it was not a word in my vocabulary. National laboratories in the United States are modulated by the science that they do, and that applies with predilection to people like us, computer scientists and applied mathematicians, and so the physical the problems of physical sciences modulate what we do, and that works very well. And it works very well because, for instance, at Brookhaven National Laboratory, it's a experimental science facility, a very, very major science facility, and it cites some of these biggest instruments anywhere. And we get to work on very, very interesting problems. For instance, we have a relativistic heavy ion collider. This is a ion smasher that very recently was awarded to be refurbished and morphed into the next generation of that, the electron-ion collider. We have a light source that at the moment is the brightest light source. There are approximately 70 beams, and each beam is a scientific universe in its own right, and each of them poses different kind of challenges of computing and data and you name it. And then a center for functional nanomaterial where there is a lot of microscopy, and I'll tell you a little bit about microscopy, but some of these newer cameras, 4D cameras, generate some ungodly amounts of data at astonishing rates. So to give you an idea, and then I'll switch to the topic at hand. In 2002, we had 230 petabytes of data. This is not data that sits in dusty tapes. This is data that has been in use. And it's not only data that is touched. This is data that, through various mechanisms, some by the decision of a group of people, such as it happens a lot in high energy physics, that decide what data is going to be needed to inform the next experiment. This data gets by some policies or automatically, and I'll explain to you a little bit about that a lot. And given that we are joined at the hip, Brookhaven, with the Atlas experiment at CERN, actually a lot of the CERN employees are Brookhaven employees that work in Geneva and experiment in Japan, Bell 2. As you can tell, in fact, the amount of data that is being analyzed is in the exabytes. So what I'm going to tell you about is just to give you a little bit of the history of modeling and simulation, not to detail accomplishments and methodologies and compare things, but to tell you that the problem that we were dealing with just a few years ago pales now by comparison with the challenges that our field needs to cope with at the moment. And also I'll tell you why artificial intelligence, not because it's fashionable and not because you need to do artificial intelligence to stay well-funded, but I'm extraordinarily optimistic that in our field, this is a game changer, and I'll try to explain a little bit why. So this is literally a 15 years old slide, which shows notionally what a performance model is. So you have two things, that you have a code and you have a system. And the system can be complicated and could be a supercomputer or could be a microprocessor, and you have a code that is running on it. And you have to get somehow, and I'll tell why, to characterize the model of that application running on that computer. And how is this done? Again, in abstract of the specific methodology. The code is characterized by data structure and decomposition and parallel activities, and you name it. And the system is, and you have to acquire these characteristics somehow. And then the system has performance characteristics that matter for that application. And sometimes you have a system and you can run benchmarks to extract those performance characteristics. Sometimes you don't, such as when you're trying to design a system and you do simulation. And I'll tell you again, I keep saying that I will. And so there are specifications to this. Performance, and this is a key thing, performance does not come from the system. Performance does not come from the application. Performance comes from the mapping of the application's characteristics onto the system resource. And that is the key. This is what performance model is a model of an interface. And then you validate the model like in all kinds of modeling and simulation endeavors. And once you trust the model, you get to the fun part to use the model. And performance models experience an exponential growth in usage. Performance models are used now in many areas. Design ahead, optimization, mundane tasks such as making sure that when you upgrade system software on a supercomputer, you still achieve the performance that you're supposed to achieve. All the way from that, procurements were extraordinarily influential because a computer system costs these days, a leading edge supercomputer is $100 million machines, and if it does not deliver the performance that's supposed to deliver, you are wasting a lot of money. So now I said that I'm going to tell you how we do that. Whereas the usage of performance modeling increased dramatically, and the community that did that in industry, academia labs, is very, very solidly anchored in the use of this methodology. On the methodology side, the field has been stagnant. Since I remember, and I worked in this field for more than 4 decades, believe it or not, that the golden standard was discrete event simulation, which can be made arbitrarily accurate, but it is impractical because to make it accurate, the computational cost of discrete event simulation is prohibitive. So you have something that in principle is very, very good, very nice, very accurate, and you start chopping it. And instead of simulating the whole system, you simulate a subcomponent of it, and you use some kind of fudge factors, engineering coefficients, as you used to call them, to take into account the sort of thing that you cannot practically do. And instead of running a big application, you're running a dot product. It sort of defeats the purpose. So to compensate, there is a whole family of analytical and quasi-analytical models and emulation. Sometimes for specific things, you burn into FPGAs, things that you can done faster, but that is very limiting in that FPGA is going to allow you to do only that for which it was. And then there are all kinds of statistical methodologies. So, enter machine learning. I have the great pleasure for the last 5 years to work on a project that is trying to establish machine learning as an alternative to discrete event simulation. There is a lot of work in acceleration of machine learning, of discrete event simulation using machine learning, a lot. You take a module in the discrete event simulation and you replace to a surrogate model. That is not what I'm trying to do. And to give you an example, a state-of-the-art simulator such as GEM5 run the simulation of a code at approximately a few hundreds of kilo instructions per second, which is 4 or 5 orders of magnitude slower than the native execution. So you can't get that far with that. And then if you were after a metric, this is a bullseye type of thing. If you're after, I'm going to design a microprocessor that has to hit these metrics. So you have to worry about circuit design, and going from circuit design to architecture, you need to do models. You have to use simulators. You have to do analytical modeling and so on and so forth. So I'm showing you here that as you go up the stack, you have to use different kinds of things in order to patch this and capture these boundaries. And if you zoom further in and you want to look at various options in doing that, this becomes quickly a problem that is not easily tractable, even when using say, an analytical model that runs lightning fast. So it's very complicated. To make things even more exciting is that performance, power, and reliability are joined at the hip because reliability you don't characterize statistically. The reliability design of the reliability gets embedded into the system itself. So you change the architecture, and I'll have comments on that. And then you have to care about life cycle coverage and so on and so forth. I don't want to go into this in. But I want to tell you that at this point in time, I haven't even gotten close to the actual explosion in complexity that modeling and simulation is undergoing. And that is, everything I talked about now is predicated on behavior that I call static. The pair code input is unique, and you have a system. And so even if you had the tools that allow you to do modeling and simulation in a practical way, you do it for that input deck and in a static fashion. You can do it a priori, not at execution time. But the workflows that I alluded to and that were discussed today in continuum computing, those are dynamic. You don't know what gets at you. So this notion that you have a unique input deck and code in the deterministic path given the input deck to the code doesn't hold true. And so the modeling and simulation of complex workflows where that gets mapped onto systems from the edge all the way to supercomputers is a whole different ballgame. And this ballgame, I think, could be very well served by artificial intelligence. So why doing machine learning-based simulation? Well, machine learning models, especially deep neural networks, have been proven to be excellent function approximators. Now, the reverse or the anti-symmetric observation is not true. Machine learning, as we all know, is good for interpolation and not for extrapolation. And this is something that we all know and have to cope for. And a very important thing is related to the explosion in use of machine learning and development of specialized neural networks and things like that. This is a virtue. This is a virtuous. We have a lot to learn from, no pun intended. And so machine learning-based simulation auto is more flexible and is highly parallelizable. For those of you that follows, I mean, probably not too many people, but there was a whole literature about discrete event simulation in the 80s, about optimistic optimization that promised to change the practicality of discrete event simulation because to what was called optimistic simulation, you would be able to parallelize somehow. But that thing collapsed under its own weight, and in fact, it turned out that each time you're trying to do that, you're changing the determinism of the problem, introducing errors that were not acceptable and things like that. All right. And now I can't advance. All right. So how we do that? I need to accelerate a little bit. This is a discrete event simulator. You have instructions. You have a traces, whatever your discrete event simulation is. What we want to do is exactly the same thing, where we place all this matching in the middle with the machine-based latency predictor, and let's see if this can be done. And this is I'll go very quickly over that. This is the first full complement machine learning simulator. It's called SimNet. It is open source in GitHub. First of all, we came up with an instruction architecture that worked well. distinguishing between fetch latency, execution latency, and store latency. And then on this side, static properties, we know all the static properties, and we found ways to deal with the dynamic property, which are the long-term history context features. In the instruction context features, we deal with the fact that, you have an L2 cache because, or an L2 miss because an L2 cache was evicted, I don't know how many instructions ago, and to the simple fact that other instructions that are not within your window, as you go to the instruction in the trace, they may have to be mapped to a functional unit that is busy. So we overcame all these things, and to give you come back to a statement that I made earlier, that is fabulous, that there is so much literature in machine learning. We found a lot of similarities between instruction simulation and computer vision. And for us, instructions are pixels, only that they are one-dimensional as opposed to two-dimensional. Instruction characteristics are, I think they are called color channels in computer vision. And this kind of CNN networks that work very, very well in computer vision, only that specialized, a little bit of a shallow version of what's used in computer vision, allows the AI to reason very well on this kind of construct of instruction. So that is, I will not have time to go on the downside of that, limitations of that, but think that they are related to the fact that given that in SimNet the instruction and architecture features are intertwined, relatively minor changes in the architecture that you are trying to predict may necessitate the retraining of the set, and that would make SimNet less practical than intended. So we came up, this is hot off the press. Incidentally, SimNet is published in Sigmetric, but this is under publication. It's a way in which we were able to decouple in performance modeling. This is called separation of concerns. We separated the workload of the application from the representation of the architecture. Each of them is represented by a neural network, and performance, just as I explained before in the classic state, comes from another network, another neural network that combines the contributions of the architectures and the network. In this case, these training sets are completely independent. The training sets for the architecture don't have to be anything fancy. We took codes from various computer science coding challenges, codes that run for a second or two. We have thousands of them. We plug them there, and we obtain very, very high accuracy on that. I'll give you one example very quickly. This is the ARM Cortex A7 processor that we simulated, and we wanted to know what would be the largest L2 cache that minimizes all minimizes the runtime of all 17 spec benchmarks. So we put that to the simulator. So we were able to do that, as you see from here. This is Gem 5, and this is ours. You see that not only we obtained the results qualitatively within 3% from Gem 5, but also qualitatively what's happening, and with a couple of orders of magnitude faster than doing. So this is a success, and since then, this is a design space exploration that is very important. I know quickly in the few minutes that I have left, the key thing that I want to describe to you. As I said, we live in a data-intensive world, and it's not only for the workflows at the accelerators where you don't know what gets at you. So the problem is now that you cannot do any kind of simulation a priori. You don't know what is the input and what kind of analysis, like in the case of scientific experiments, what kind of analysis will have to be triggered, where those are going to be executed, and what is the role of various sensors, for instance, within the accelerator, sensors for control, sensors for optimizations, sensors for physics, that refocus the cameras, and they can change dynamically what's going on. That is a major challenge. It's one of the most important challenges. So we have this, we coined this term dynamic modeling, very, very much related to what I learned today about continuum computing, where the dynamic modeling not only assembles models on the fly, so you don't have the luxury anymore to do a discrete event simulation or to create because you don't know what are you modeling. So the models have to be assembled on the fly. They have to be lightweight. And because many of these, as I'll show you, many of these instruments have to be refocused for the reason I'll explain, you need to use a framework of supervised learning because in that way, if you have a reference model, you can make the models assembled at runtime, you can make it actionable. And the implications on that go way, way beyond experimental facilities. This is how, in actual fact, you can combine systems that are socio-technical. And so we are using this methodology not only for the accelerators at Brookhaven, but for uses in Department for Homeland Security, where I think Eva or someone discussed fires, or so things that you can morph to being actionable. Here's a few quick examples. This is a 3D camera, 4D camera microscope. This generates 50 megabytes per second, and you have to capture 50 megabytes per second on sequences that are 10-15 minutes long. Just think about the amount of data. And because probes are either perishable or expensive, and because microscope time is very expensive, you need the ability that within those 10 minutes to refocus the camera, they can be refocused through currents. And so you need not only to capture that data and avoid to drop on the floor, but assemble a model, and the model becomes introspection for a runtime system that does that. So the challenge is extraordinary for this kind of modeling. This is the accelerator at the latest accelerator at the latest detector of the accelerator. This will become the detector also at the next experiment at Atlas at CERN. This generates 100 terabits per second. And it has to be zero suppression initially. So all of this is co-designed, modeled. These ASICs, there are hundreds of ASICs, arrays of ASICs that are done locally, fabbed locally. And then there is an optical network, which is also designed locally with a proprietary protocol. I don't know why it's... And then slowly, you get into the comfortable zone in which data is in some storage, and then you send it on a supercomputer. And if it's for CERN, there are thousands of supercomputers in hundreds of locations all over the world with so on and so. And to put this in perspective, the holy grail is that this is the accelerator, and this points us towards digital twins and autonomous facilities. We have this integrated modeling and simulation environment, which is the brain of all this, that needs to do monitoring, modeling, management, and mitigation and optimization. And this is everything that comes into it. Incidentally, at this accelerator alone, for control, there are 200,000 sensors for control alone. And there are many, many orders of magnitude more sensors for the physics. So the idea is that the dynamic modeling through machine learning to be able to take us towards autonomous facilities and digital twins. This is not new. For instance, I don't know, Bill, if you ever saw that, this is very, very interesting work for neural network for device placement on your cloud. The idea here is I'm running very large scale AIs, and I want to minimize data movement. So I want each layer of a neural network to be computed into GPUs that are physically adjacent or close by. This is work by Azalea Rossini, who's now at Stanford. It is basically a way of doing graph partitioning to the machine learning, and we in computer science said that we know how to do graph partitioning. We never did. No, graph partitioners were notoriously imperfect, but this is done now. However, this is, again, to my taste, this is not dynamic. This is static. All this mapping is done a priori, but apparently it showed, I can quote the paper, that they improved the efficiency by 60% of these runs. So this is very wonderful. However, this is very different because different parts of the neural network or an experiment could require different mapping. So the way to go is to do. I see movement. Two more slides very quickly. One is distributed resilience. These systems have to be engineered for resilience. You cannot ensure redundancy. Resilience done by brute force redundancy is not going to cut it. You have to tackle the problem of resilience in concert with that of data traffic minimization. And actually, that's a great idea. I have a very big project now from DOE Oscar on that, dealing with the CERN experiment. And I think this is the way to go, and it will lead to potentially methodologies to do that for other complex workflows. And finally, this is part of a bigger thing called optimal design of experiment, where exactly as Karen talked about yesterday for digital twins, this cannot be done without uncertainty quantification and verification and validation, because none of these modeling methodologies, let alone machine learning, has any kind of error bounds that are practical. So you have to be careful. So I'll leave you with that. I think this is for real. This is not, and it's going to tremendously to lead to tremendous advances in co-design. For me, people talk about co-design in many ways, and everybody's right. To me, co-design is the quantitative tools of it. Think about one. I'll leave you with one thought, right? So we take an application and we generate a training set. We take an architecture. We get characteristics. We do machine learning. But machine learning is smart, but it's dumb too. We are doing this for RTL. We can go down the stack without having to go to all those tools. We could, people say, well, we'll co-design from the materials up. Yeah, that's the way to do it, I think. And because that's the, again, I have a very optimistic outlook on that. Thank you.